Greetings, everybody. So the topic of today's video comes from a recent conference, DANOC, on Days of Applied Nonlinearity and Complexity. And what we are going to talk about today is key concepts for introducing chaos theory to secondary education. Okay. So basically, our discussion is going to be about whether it is worth or not introducing the concept of chaos in secondary education, and why we should do that. What should we teach and how should we teach it? Okay. So let's begin, of course, with a general introduction about chaos and why should we teach chaos theory. Now, I assume many of you coming to this video are probably somewhat familiar with chaos. Okay. So chaos is all around us, right? Since the 60s, there have been papers talking about chaos in physics, in engineering, so either man-made systems or natural systems. In biology, in economics, like supply chains, biology, for example, predator-prey models. In chemistry, in laser and sync, and in circuits, all around us, there are chaotic systems being reported. So I could easily say and make the argument that pretty much all systems in nature are chaotic. And of course, this is true. I mean, I doubt if you try and find a completely linear system in nature, you're not going to find it. Okay, unless it's like in a very controlled environment. Okay, so chaos is all around us. And of course, apart from the physical interpretation of chaos, especially the last 20 years or so, there have been applications of chaos in bit generators, in encryption. Of course, we do that in our research problems, in watermarking, in secure communications, in chaotic optimization, in chaotic path planning, and exploration and surveillance, and even more applications that I even don't know about all of them. So many applications consider chaos as well. So really, it has found a lot of use in the literature. Okay, so since chaos is everywhere and since chaos is applied to so many different disciplines, there is a natural question here. Why don't you teach it? I mean, you teach it sometimes in universities, like in physics departments and maybe in mathematics departments, but why not introduce it further in secondary education, But it's all around us. Why don't do it? Right. Well, of course, there is a simple answer to that. We don't do it at the moment because it's not an elementary topic, okay? So it's not easy to talk about chaos analytically. It's a very difficult concept. But this is a fair argument. At the same time, though, there is a counter argument that is also very fair, that since chaos is all around us, probably you can explain it because it exists so many different levels and physical phenomena. Probably you're going to be able to talk about chaotic phenomena without going too much into details. Okay, so for example, you can use illustrations, pretty much like I'm going to show you. You can use graphs to illustrate chaotic behavior, okay, or periodic behavior, or phenomena relevant to dynamical systems without going into details. And this is a very fair argument, okay. And we can build upon this argument to actually try and introduce the concept of chaos in secondary education, okay, and not wait until university. For me, there are many expected merits for this, okay, for physicists, for mathematicians, for all the people in the natural sciences alike, okay. The reason being is that by teaching chaos, you kind of unify all the natural sciences, because as we said, chaos exists everywhere. It exists in paper, in mathematics, but also in biology, physics, engineering, whatever. So you can unify natural sciences by talking about chaos, which is a universal phenomenon. Okay. One might argue that by teaching chaos for physicists, you provide the mathematical support for it and the programming support for physics, right? Because you can supply and support your evaluations either through mathematics or through programming and simulations. And of course, whether you like it, I guess you're going to like it. You can make the exact opposite argument that you can have a physical and programming support of mathematics by teaching chaos to mathematicians. Okay, to mathematicians, sorry. Of course, so both arguments are valid here, of course. And moreover, you can have a great passage to higher education, right? Because it's an advanced concept, but by teaching it at an earlier stage, I'm sorry, you can actually draw people to the natural sciences. So it can serve as a passage to higher education. Now, what should we teach, in chaos, and what to teach and how to teach it? Of course, this is not an easy task. There are many concepts in nonlinear dynamics in general that you should teach. So what I did here is make an initial try and identify some key concepts in dynamical systems. And I separate them in introductory concepts, advanced concepts, and of course, we have the hands-on projects, okay, that have to do with creating chaos yourself. The idea is, of course, to give emphasis in examples, so use less mathematics here and less rigorous uh, descriptions, but more or less give the impression or the understanding of the physical phenomena. Okay. And of course, it is worth noting here that this is a very active research field. You will find many publications that have already considered this problem in secondary education. And we actually have so specifically some papers from Greek people here. And of course, the same thing has been done with control theory. It's also worth noting because the basis of control theory is dynamical systems. So people in control theory have also done similar tasks themselves. So let's start by talking about the introductory concepts. Okay. The most basics for me are, of course, the distinction between continuous and discrete time. Okay, super basic. Everybody needs to understand the difference between these two types of time understandings. And of course, the further, most basic properties of systems is determinism, okay, super basic. Causality, of course, super basic to know when a system is causal or not. And of course, time invariance, okay, very basic property, as you know, in understanding chaotic behavior. So we start by this very basic phenomena. The second step of basic concepts, of course, has to do with the general property of a system. So we need to understand what is a system, what it consists of, how is it separated from the rest of its environment. I have a couple of systems here. Of course, by talking about systems, we open up the discussion about degrees of freedom. I mean, how many variables do we need to describe the system? For example, this single mass here, is the single, a double degree of freedom system, a triple degree of freedom system? So it's very important to understand what a degree of freedom is or what the dimension of a system is. Okay, so discuss about, how many quantities can change independently in the system. And again, of course, after we explain all this, we open up the discussion on the very basic property of state space. Okay, super important definition. People from control theory know this as well. To understand the system, you need to be able to understand what is the state space of the system, right? For a single mass or a double mass system or more masses, it's very important to understand the quantities that you need, the variables that you need in order to describe it, right? And of course, after you do all that, you can talk about the solution of a system. Okay, I would advise calling it the trajectory of a system because we need to have a geometric understanding of the system's solution. So whether you like it, I mean, you can call it the solution of the system, but it is much better if you call it the trajectory of a system, right? And of course, we're ending up with the super basics like talking about linearity, possibly talking about memory in a system. Okay, I guess people working in circuits are going to be interested in that because they may want to talk about memristors, for example. But of course, linearity is a super basic property, so you need to explain it. Okay, the superposition, as someone called it. And the final topic that I consider to be introductory is the phase portrait. As you all know, it's extremely important to understand dynamical behavior and chaotic behavior. I need to remind everybody, okay, when we have the solution of a system and we plot each state over time, as you see right here, for the state and for the displacement and the velocity, the phase portrait plots the states of the system, not with respect to time, but with respect to each other. So you obtain something like that. And this is a very nice graph in explaining behaviors like this mass spring damper here, or a pendulum, or, in general, systems that have oscillations. And of course, it's a topic that's worth noting in chaos systems as well. So extremely important concept. And this is where I stop with my so-called introductory concepts. Okay. By walking into advanced concepts, of course, we assume that everybody has understood the previous series of ideas. So now we can discuss about nonlinearity and whether the system goes to a steady state by oscillating or by not oscillating, or maybe it goes to infinity, okay, as you see on the top graph right here. And the best way to that and talk about stability and non-linearity is to introduce, you know, these sort of robotic systems that I have here. You can call them robotic manipulators, you can call them pendulums, whatever suits you better, you know, they are both correct. And of course, this opens up one of the most basic concepts in nonlinear systems and chaotic systems, which is the concept of an equilibrium. Okay. So for me, these two graphs are great for explaining equilibrium and stability of equilibria, because as you know, this pendulum here, or a robotic manipulator, has more than one equilibrium, has a stable and an unstable one, and the same one holds for this double pendulum here, which has 4 equilibria. So I think this is a great way to discuss stability and equilibria and non-linearity, because here we have rotational motion. Okay, so cosines are involved. And of course, possibly open up to the concept of basis of attraction, which is extremely complex, but through these examples, I think they can be easily understood, right? And of course, the second step in the advanced concept is talking about chaos. After we have explained all the previous things, we can start by discussing about periodicity and the levels of periodicity, exactly like I have here in the bifurcation diagram. So period 1, period 2, period 4, period 8, and so on. And then we can begin talking about chaos through sensitivity to initial conditions and discuss the transition to chaos. Okay, so as a parameter changes, how does the behavior change and little by little goes into chaos? Of course, we can do all that through the bifurcation diagram. And the question that rises here is whether we should do it in continuous systems or discrete systems. Okay, this is up to you. I think, and probably you will agree as well, that the best way to explain these behaviors is initially through discrete time. Because in discrete time, so the solution is much more easier to explain. We have a simple time series. We can explain periodic behavior very, very easily, because it's, you know, even in the graph here, you can see it. While where we are going to discuss about chaotic systems in continuous time, in order to explain periodicity and chaotic behavior, you need to introduce the Poincaré section, which is a much more difficult concept. But you can do that at a later stage, okay? And of course, then you can talk about all other phenomena like coexisting attractors, etc. So I have this bifurcation diagram here for the Lorentz system as an alternative to the logistic map, so you can use that as well. And then, of course, talk about symmetry or coexisting attractors, which is another more advanced concept. So the last part is hands-on chaos. Okay, here, of course, it depends on the department that you are stationed at. Potentially, you can let the students create their own chaotic system. Okay, there are many examples. For example, this double fidget spinner here, or the double pendulum you see on the left. I have links to this YouTube video. And of course, if you are in an engineering department or you have an engineering background, maybe you can create a chaotic system yourself, okay, and show it to students. I mean, I haven't done that before, but I think it is possible to create a very simplistic double pendulum using some very basic, you know, off-the-shelf products. So this would be an extremely nice example to show to students and understand hands-on what is a chaotic behavior. But you can do other stuff as well. Okay, for example, you can simulate chaotic circuits. If this is your background, for example, some people in the lab here are very familiar with emulating chaotic systems in circuits. You can do some random bit generator using Arduinos. And if you don't want to use Arduino, you can actually do it by simply programming in MATLAB. So again, this is a very nice example to show to students how we can use the chaotic system to our advantage. Okay, for example, create a random number generator. Or of course, if you're in a more advanced background yourself, you can create something like a chaotic laser. I'm totally unfamiliar with this, but I know it is possible. Okay, this would be an extremely advanced, of course, hands-on application. I'm not sure if secondary level students will understand that. But for example, a random number generator, I think it's much easier to understand. So some closing remarks here. We have a series of topics that all of them together give us a great understanding of chaotic behavior and its applications. They're separated in 3 different categories, but of course, you don't necessarily need to teach everything, okay? Depending on how much time you have, you can make some option here and choose a subset of these topics, okay? I would suggest always talking about continuous and discrete time and determinism. It's very basic. Talk about the trajectory of a system. Again, it is very basic. And then talk about equilibria, which are very basic in understanding a physical system. And then possibly talk about periodicity, sensitivity to initial conditions, chaos, and show the bifurcation diagram, but in discrete time, which is the easiest to understand, right? And as an application, again, it has to do with your background, but I would probably choose a random number generator because it is very easy, just a few lines of code in MATLAB, you can do it, or in any other programming language. And of course, if you have the skills, you can possibly consider, creating a double pendulum. So many topics, and I would say, depending on your own background, you can choose any of these and teach yourself in the future in any secondary education level. But you need to go by your students' needs. Okay, so depending on the background of your students and the abilities of your students, I would say just nitpick only the topics that you find to be the more suiting for your students. Okay, and only teach that. Okay, of course, the idea is to create simulations for all of the above topics and concepts. We have a lot of simulations here creating ourselves. So I will also put a MATLAB link down below where you can download some of these diagrams. And any other thing that you like, you can simply email me and I will try to provide you with some help in designing it. Of course, we have a YouTube channel apart from my own where we discuss about these things, so you can subscribe there as well. So thank you very much.